Hey, good morning. Previous class in the electrostat, we are discussing about electric field in material space. We consider we have classified. We have sorry, we have looked at the classification of material from electrostatic perspective, like insulator or dielectric and conductor, and then we focused much into the dielectric part. So when the electric field is applied to the dielectric, the phenomenon called polarization has been discussed. So now next topic is boundary condition or interface condition. The idea is in this particular module is we are calculating the electric field, or we are considering, or we are analyzing the electric field in the real world material. Instead of considering in free space, we will consider the conductor and non-conductor, insulator or dielectrics, all these different sort of material we will consider, and we will try to understand what will be the electric field. Will it undergo any change, or it will remain same? All this we will try to study. So this topic title is boundary condition or interface condition. So as name implies, boundary or interface. So this is applicable when if field, if electric field exists in a medium. Earlier we consider homogeneous medium. Now let us consider a non-homogeneous medium. In a medium which is non-homogeneous medium, which contain two different dielectric. Earlier we consider in the first two models we consider only free space. Then in the past few meetings we have considered relative permittivity epsilon r, but we consider only single medium. Now we'll consider two different mediums. Okay, so if electric field exists in a medium which consists of more than one, like consider two mediums, two different medium, then the condition that the electric field should satisfy at the interface or boundary is called as boundary condition. Simple picture, assume electric field exists, is electric field which exists in medium 1, or let me redraw the picture. Consider this is medium 1 and this is medium 2, and this medium 1 and 2 should be characterized in terms of electric field. If it is in terms of electric field, then it should be characterized with the permittivity. So you can say epsilon 1, and medium 2 can be characterized with epsilon 2, and this line which is separating the dark line which represents, this is the boundary. Okay, the black shaded region is medium 1 and red shaded medium is medium 2. Both has different permittivity. That's why we call it as different medium. So in this case, we consider two medium, and these two mediums are meeting at the boundary. So what should be the condition that electric field should satisfy at the interface? Let us say we have some electric field exists, or electric field is passing from penetrating from medium 2 to medium 1. So, consider some random electric field which is oriented in a random direction. Then when it is passing from medium 2 to medium 1, will it undergo any change? Like light, when it is passing from one medium to other medium, and if the medium is different, then it will undergo some change in angle, right? So it won't go straight. It will change. So the diffraction, how much will be the diffraction? All this we need to understand. Or now few questions like in medium 1, let us say this is electric field 1, and medium 2, now let us say it is it is 2, right? So it is bottom side, it is medium 2, upper side, let's consider medium 1. Now the questions are like, what will be the magnitude relationship? Whether electric field 1 electric field in medium 2 and electric field in medium 1, both are equal in magnitude. and what will we don't know this relationship that now we are going to establish. And same way, what will be the direction of electric field in medium 1 and medium 2? Whether both will be in same direction, or will it undergo any change, or whether the as it's penetrated from medium 2 to medium 1, will it bend toward boundary? Will it bend toward boundary, or will it continue in same direction? Okay, all these things we want to understand. So application of this topic is if you see this boundary condition, I'm repeating, boundary condition is the condition that electric field is supposed to satisfy at the boundary or the interface, where interface is a meeting of it is a junction of two different mediums. You can have a number of medium, but always we will consider two mediums, and at the interface we have to apply the boundary condition, or we need to calculate the boundary condition. So if you know the application, if you know the boundary condition at the, or if you know the condition, then the application of this approach is we can calculate, let's say if E1 or electric field in medium 1 is known, then you can calculate the electric field on the other medium. It's very easy to calculate because already with this boundary condition, we know how much will be the change, what will be the direction of bending, all this information we will aware of. So if you apply those conditions, then you can predict or you can calculate the electric field in the unknown medium from the known. This is one approach, one application. Okay, then I think we can take it as a major application. This is more important for in the computation field called as computation electromagnetics, where we will know only about the source, or we know only the field at some certain region, and we want to calculate the field at the other region. To calculate that, we have to apply the boundary condition. So this boundary condition, it's somehow somewhat similar to the boundary condition what we have studied in mathematics. So only at the boundary, let's say this is boundary. At the boundary, you know the details, or you know the conditions to be applied, or conditions that can be forced. So if you know the boundary condition, you can able to predict what will be the field on the other side, provided that field on one side is available. So with the boundary, we are calculating, it helps us to calculate the field on other side. Now we will consider different combinations of medium. We have classified the medium into free space, dielectric, and conductor. So we will consider three cases. In one case, or in the first case, we will consider a boundary or interface between two different dielectrics. Let us say epsilon R1, epsilon R2. Second case, we will consider dielectric and conductor. If it is dielectric and conductor, let us say at medium 1 is a dielectric and medium 2 is a conductor. If medium 2 is conductor, then you can put electric field equal to 0. So this is conductor. The problem will be quite easy. Okay, so in this case, this is dielectric 1, and this is dielectric 2, this is dielectric 1. Third possible combination is dielectric and free space. Epsilon are equal to 1, equal to 1, right? So in this case, it will not be equal to 1, some other value, it's greater than 1. So this is dielectric and free space. So the solution is going to be a one line, very small equation. And if you understand this particular topic, that is first combination, that is two different dielectric boundary condition for the two different dielectrics, then that's more than sufficient to understand the remaining two topics. Even you don't need to memorize the equation, this is more than sufficient. And you will get 1 10-mark question from this CAT, and also in the FAT exam, you will get one question. Compared to the other topics in electrostatics, it's quite easiest one. Now let us start with, let us calculate the boundary condition for dielectric boundary. Let us say dielectric 1, it's characterized with epsilon R1, and other dielectric medium 2, This is characterized with epsilon r2, dielectric 1 and dielectric 2. Let's assume this is a boundary. This is medium 1, this is medium 2, and medium 1 is characterized medium 1 is characterized by the permittivity, relative permittivity epsilon r1, and medium 2 is characterized with permittivity epsilon r2. Assume electric field vector. You can take any orientation. See, this red is the boundary. Assume electric field is the field is passing from medium 2 to medium 1. So medium 2, let us write it as E2 vector, and medium 1, let us say it's E1 vector. We assume like it's passing in this direction. Okay. Now for doing the analysis, what you need to do is you need to decompose this field into its orthogonal components. Two orthogonal components, that is tangential component and normal component. You can write E to T, T for tangential or tangential to the boundary, and E to N. E to N means electric field 2, which is normal to the or perpendicular to the boundary. So just what we did is we just decompose this into orthogonal components. Again, decompose this into its orthogonal components. E1T, E2N, sorry, E1N. Now we need to find the relationship. What will be the electric field or tangent? See, we cannot directly find the relationship between electric field 1 and electric field 2. We need to decompose this into the component which is parallel to the boundary and perpendicular to the boundary. Then only we can able to solve the problem. Now let us consider to solve this. Let us consider or let us apply the known equations. One equation is electric field in a closed loop is 0. E vector dot dl vector is 0. Electric field in closed loop is 0. Now let us apply this condition or apply this equation for this medium or for this two medium combination. Now let us first construct the loop. So this dl is the closed loop. That's what we have constructed here. Let us say the length is L and height, this height is delta h, half delta h, and again this is half delta h. If you apply the now we can apply this. If you apply, now what you need to do, you need to do the dot product between the electric field and this displacement. Now let us start. First start with this E1T dot product with dl. So you need to take the dot product between the parallel vectors. So you can see the with this vector E1T, the parallel vector is, this is the parallel vector or displacement vector which is parallel to that. So E1T multiplied with L plus, you can see the other vector electric field is, which is the normal vector, that is E1N dot product with this displacement length. This length is delta h by 2. But you can see this vector displacement is in this direction, but electric field is going in the upward direction. That's why we are keeping a minus sign. We are putting a minus sign. Now continue to this segment. This segment length is delta h by 2. Multiply with the electric field. But now we are in the medium 2. So in the medium 2, parallel to this, you have this vector, that is E2n vector. So that is E2n but you can see the electric field and displacement is in the opposite direction, so minus sign. Continue with this segment. So this segment, the length is L, and you need to do the dot product with the E2T, and both are in the opposite direction, so you need to insert a minus sign. Now continue to this segment, delta, I will continue here itself, delta H over 2, and parallel to this electric field is E2N, and both are in same direction, so plus sign. Continue with this segment, the final segment, E1N, which is parallel with L, or this segment, which is equal to 0. You can see, notice this normal component E1, this, and it is E1 and oh sorry, this is not L, this is H by 2, right? So these two will get cancelled. Same way, these two will get cancelled. The opposite sign. So what remain is 1 E1T minus, sorry, into L minus E2T multiplied with this length equal to 0. I can say E1T equal to E2T. So this is what the condition, or by applying this equation, we found one relationship, that is tangential component of, I will write the confusion here. You need to please try to interpret the meaning of this equation, E1T equal to E2T. The meaning is electric field or tangential component of electric field is continuous across the boundary. Boundary or interface. That means tangential component in medium 2 is available, because it's assumed that it's passing from medium 2 to 1. So in medium 1, the tangential component will remain same. It will not undergo any change. That's what you need to understand. Any questions? So now we have found the relationship between only the tangential component. Still, we need to find the relationship between the normal component, or the component which is perpendicular to the boundary. Is it clear?
Yes, sir.
Now, thank you. Now we will continue with this. Consider the boundary, medium 1, medium 2. We need to calculate the, let us see what we need to apply. Now let us apply. See, apart from that, what equations we have in terms of closed line or closed path, we have one equation is closed line integral of v dot dl equal to 0, that we have applied, and other equation is from the Gauss law. We have this d vector dot ds vector is q enclosed. So let's try to apply this. See, the reason why we are applying this is we can this contains some closed path or closed line, so we can keep that closed path or closed line which is exist in two mediums, and we can find the relationship, because that medium is continuous, like that whatever the closed surface or line you are keeping, that is continuous in these two mediums, which exist in both mediums. That's why you try to consider that previously E del closed line integral v dot dl is 0. In this case, we will keep this equation. We will try to apply this equation. Now let us apply. So medium 2. It is instead of writing electric field, now we can consider electric flux. So let us say d2 vector. This is d2 T. This is d2n. This is d1 vector. This is the component which is parallel to the boundary. This is the component which is normal to the boundary. Now we need to apply this Gauss's law. For that, you need to construct a closed surface which should exist in both mediums. You can consider a cylinder. Let's consider a cylinder here, and say the cylinder surface area, top surface area is delta S, and bottom surface area is delta S, and then surface vector normal to the upper this top plate is, let us say, delta or AN. Then for the bottom surface this should be AN, right? Because if you take this as a positive axis, z axis or a positive axis, then if you consider this AN, then this should be minus AN. Sorry, it's not plus AN. It should be minus. Sorry, plus AN. So this is plus AN, then it should be minus AN. So this surface area is delta S. The height is total height is h. Let us consider delta h is the total height. Now we can apply this equation. If you apply this for the closed surface, you have to apply, or you need to evaluate this integration over the three possible surfaces. One is top surface, another one is bottom circle surface, another one is a cylindrical or circular surface. Three surfaces you need to consider. But anyhow, in this case, we will consider only top and bottom surface with the assumption that delta h should be 0. That means if you want to, if you see in the previous case, we have not considered it, but anyhow, the term is get cancelled. The height, we consider some height, right? This height we have considered. What should be the height? Height of the loop. Length of the loop is delta L, that's fine. But what should be the height of the loop? The height of the loop should be infinitely small. Then only you will represent a boundary. Okay, so we will assume that delta h or height of the cylinder should be as small as possible, or delta h tends to 0. In that case, you no need to evaluate through the side surface. Okay, even you do it, it will become 0. Let's not do that. So now let us only evaluate the integral through the top and bottom surface. Now for the top surface, this is the surface vector, and parallel to that, this is the vector. So D1N, which is parallel to delta S. What is this surface vector? What is the surface? This is delta S along NKN, right? You can write delta S. Same way for the bottom surface, D2N. This is D2N, but it's going in this direction, but surface vector is in the opposite direction. That's why we need to insert a minus sign. And the surface area is delta S, which is equal to, now this is the question, what is the Q? What is the Q enclosed? See, the Q enclosed, in this case, it is a dielectric medium. We can put it 0 here. Now, let us assume we are deliberately kept some charges here. If somebody kept the charges over there, then we can consider it is some charges Q is there, and Q is rho S into delta S. Okay, that because let us say this charge, see what you are seeing only the side view. Okay, so this charge, whatever I have represented there, it need to be represented with rho S, that is coulomb per square meter. Surface charge density will be defined. So in the problem, surface charge density will be given. So from the surface charge density, how will you calculate the total charge enclosed by the cylinder? You need to multiply with the surface area, delta S. See, you need to clearly understand the problem, whether charge, if it is given, you can take, otherwise you can force it to 0, rho S equal to 0, you can make it as 0. Now we can say, we can finalize this equation, D1N minus D2N equal to rho S. Or if there is no charge exist, if it is pure dielectric medium and if there is nobody kept any charges over there, then you can consider rho S equal to 0, and you can consider this equation D1N equal to D2N. That is, normal component of electric flux will be continuous across the boundary. Normal component of electric flux or flux lines, you can take it as consider as flux lines. The flux lines which is perpendicular to the boundary will continuous across the boundary. Continuous means it won't undergo any change across the boundary or interface. Now let us consolidate the two boundaries. See, what we have considered is two dielectric medium. We have considered a boundary which is the meeting point of two dielectric mediums, epsilon R1, which is characterized by epsilon R1 and epsilon R2. Then we have tried, we have calculated, we have applied the governing equations like in the closed path, electric field will be 0. Then we have applied the charge enclosed by a closed surface equal to the charge enclosed. So all this we have calculated, applied, and we got this equation. One is E1t equal to E2t. That means tangential. You don't read like E1t equal to E2t. Simply you can recall this as tangential component of electric field is continuous across the boundary. Boundary means it is meeting point of two medium, 1 and 2, or it can be A, B, anything, any name you can put. And other condition is normal component of electric flux is continuous across the boundary, provided that rho s equal to 0. From this you can even write one more equation, D equal to epsilon E. I'll write it here. D equal to epsilon naught into epsilon R into E vector. Right? In this case, or you can say E equal to D over epsilon naught into epsilon R. So E1t can be written as D over epsilon naught into epsilon R1, which is equal to D2t over epsilon naught into epsilon R2. Or in this, any of this 2 will get cancelled, right? Epsilon naught term will get cancelled. So you can simply write D1t over epsilon R1 equal to D2t over epsilon R2. So the meaning of that equation, this relationship is tangential component of electric field is continuous, but tangential component of electric flux is not continuous. Correct? It is not continuous. You can see it's a function of, or it depends on the value of epsilon R1 and epsilon R2. It is not equal. Okay. Same way here, if you apply the relationship D equal to epsilon E, you will get epsilon R1 into E1n equal to epsilon R2 into E2n. So again, from this, the normal component of electric field is not continuous, and tangential component of electric flux is not continuous. See, don't remember these two equations. No need to memorize these two equations. Just keep these two equations is more than sufficient. Equation 1 and equation 2. So with this, whatever we found is what will be the magnitude relationship. Let us say on one side, let us some magnitude, and what will be the magnitude on the other side. So that's what we found. Now the direction, what will be the direction change, or what will be the refraction? You can think of the light example. When it is passing from one medium to other different medium, what will be the refraction? What will be the bent of the field? That's what we are going to calculate now. One information. Next class, I think next class is on Thursday, right? Thursday between 10 to 11. 10 to 11, I have exam duty, so there will be no class, but quiz will be conducted between 10 to 10:20. I will share the link. It's very similar to your quiz one, how it is conducted. The same way the other quiz is also conducted. Quiz portion is your entire CAT 1 portion. I'm repeating, that portion is entire CAT 1 portion. I will share the link just before the. I will share the link even in advance. I will share the link in Teams. In order to join the meeting, there will be no class zone this Thursday, coming Thursday, 10 to 11. Now I will share this detail in Teams also. So next we need to calculate what will be the bend that we need to calculate. Better I can draw a separate picture. See, this is boundary. This is normal to the boundary. This black line, this vertical line is normal to the boundary, right? Line which is normal to the boundary. Let's mark this angle as theta. Theta is the angle between the vector which is normal to the boundary and the electric field or the field. Please understand this point clearly. Theta is the angle between the electric field and the vector which is normal to the boundary. We are not measuring with the boundary, along the boundary. Sorry, it is not the angle between boundary and the electric field. Keep this point clearly, because while solving the problem, sometimes you may need to calculate the angle with the boundary, or you may need to calculate the angle which is making with the normal to the boundary. To avoid this confusion, let us mark this as alpha. This is 90 minus theta, right? Same way, this, let us say this is alpha. Alpha is medium 1, right? This is medium 2. So let us say this is alpha 2, this is alpha 1. Really, this is what you need to understand. Now let us apply or let us see how much bend it will undergo. So this is medium 2, epsilon R1, this is epsilon R2. Now let us write the equation. You can say this is E1 So we are writing in terms of theta 1. Let us write in terms of theta 1. Because usually we used to measure in all problems, if the angle is given, that will be theta. It will not be alpha. Just for your understanding, I am just putting alpha here, but theta will be the given value, and theta will be the angle between the vector and the vector which is normal to the boundary. Now let us write the equation. See, this is, what is this one? This is E1 into cos of 90 minus alpha, right? This is E1 into cos of 90 minus theta 1. So cos of 90 minus theta is sin theta, right? Now, sorry, I think not started thing. Sorry, now let us apply the boundary condition ET1 equal to ET2. Now, let us apply this boundary condition ET1 equal to ET2. So this is ET1, right? So this is ET1. So ET1 is E1 sin theta 1, which is equal to ET2. What is ET2? This is ET2, right? So this is ET2. Or you can say this is ET2. Right? What is ET2? ET2 will be this is E2 vector. Then ET2 will be the same way, it will be E2 sin theta 2. Right? ET2 is E2 sin theta 2. Is it clear? It will, I think it's a quite simple equation, right? Okay. So next, apply the other boundary condition dn1 equal to dn2. Assume there is no charges available at the boundary, then you can take dn1 equal to dn2. So in this case, um, um, so that's normal component, right? This is normal component. Assume that instead of E, now consider it as D. I don't want to draw a separate picture, but if you want, I can draw a separate picture here. This is D1 and this is theta. This is the normal component, right? So this is D1N, this is D1T. So now, what is dn1? dn1 will be d1 cos theta 1. Same way for d2, you will get d2 cos theta 2. So D1 is now, see, we have the equation, but we want to try, we try to relate these two, or what will be the um, um, bent angle bent by the electric field, sorry, the amount of bent experienced by the electric field. So you need to express this D in terms of E. So D1 is epsilon R1 into E1 into cos theta 1 equal to epsilon R2 into E2 into cos theta 2. Is this clear? See, this is theta 2. Sorry guys, I think in the second we are writing En, right? For normal component we are writing, right? Oh, sorry, this picture is here. Sorry. See, for the second, for the normal component, you need to consider this picture. So while explaining, I have considered this one, so I think there will be no confusion. Now we have two equations. Now we can take the ratio of these two equations. If you take the ratio of both, then you will get tan theta 1 over tan theta 2. If you take if you take the ratio of these two equations, then you will get tan theta 1 over tan theta 2 is epsilon r1 over epsilon r2. So the idea is, if the electric field, let us say in medium 1 or let us say in medium 2, the electric field, the angle which is making with making with normal to the boundary is given, let us say theta 2 is given, then you can calculate what will be the bent angle. This theta 1 you can able to calculate. Theta 2 will be given, theta 1 you can able to calculate, and that will be a function of this medium parameters like epsilon r2 and epsilon r1. Hope this is clear. So these three equations are important. One is, you can say, equation 1, equation 2, and equation 3. These three are more than sufficient to get 10 marks. Any problem which is related to the boundary condition. Hope this is clear. No questions. I will move to the other two medium combinations possibilities. So combination 1, it is epsilon r1, epsilon r2. Medium, that is second combination, possible combination, we will take epsilon r1, and this is conductor. That means conductor means conductivity should be equal to infinity. So it's a conductor. You can say the conductor. So in this case, it is dielectric. When you will call it as dielectric, when the relative permittivity is greater than 1, you can call it as dielectric. Otherwise, you can call, if it is equal to 1, you can call it as free space. So third possibility, a dielectric, epsilon r1, and other side is free space, that is epsilon r equal to 1. Sorry, epsilon r2 equal to 1, that is for free space. So it's free space, and one side it is dielectric medium. So already we have established, and we have this equation ET1 or ET of ET1 equal to ET2. Then for a normal component, dn1 equal to dn2. Or you can take other possible equation is dn1 minus dn2 equal to rho s. see this while solving the problem, we will into confusion like dn2 minus dn1 or dn1 minus dn2. That's related to the problem. You need to carefully look at the problem. So electric field is going in this direction, or electric field is pointing in the opposite direction. That matters. So don't think this as a universal equation that's related to the problem. While solving, I will explain it. Now let us for this moment let me ignore this equation. Now let us rewrite the same equation for other boundary combinations, like for a dielectric conductor. That is second possibility. You already know that if it is inside a conductor, electric field will be zero inside conductor. I think I have not discussed this. Now for this moment, you assume electric field inside the conductor will be zero. There can no electric field survive inside the electric field. Simple relationship. In a conductor, potential difference will be zero in any conductor or equipotential body. And this relation E equal to negative gradient of V. Okay, so if there is potential is zero, then electric field will be also zero. So electric field inside conductor will be zero. Now, if you apply this condition into this equation, so this equation will become, can you have to tell this equation? See, E2 equal to 0, medium 2, electric field in medium 2 is 0. Either tangential component or normal component, whatever it is 0. Now, can you rewrite this equation? You have, this is for general, like for dielectric, you have the you have the relationship. Now, apply this condition and rewrite this equation. Et1 should be equal to 0, right? Because this part is 0, this part is 0. That's all. Same way here, dn1 equal to dn2. So if electric field is 0, then there will be no magnetic field component, right? Again, you can simply write dn1 equal to 0 from this equation, right? dn1 equal to 0. Or maybe if you consider this second equation which I have striked out, you can say dn1 equal to rho s if there are some charges. Now you consider some conducting medium, right? So maybe if charge value, surface charge density is given, let us assume that like there is no equilibrium state reached, and let us say there are some charges available to the surface, then we can use the second equation. So in that case, dn1 equal to rho s. Or we can say the important point is epsilon r1 into En1 equal to rho s. You can see electric field only perpendicular to the conductor. So keep this point in mind. If you have any conductor, let us say it is a conducting medium, if some slab of conductor. So electric field can survive only when if it is perpendicular to the surface, En. But if the electric field is parallel to the conductor, it will be zero. Tangential component will be zero because it is like short circuiting, right? So electric field is like plus minus. Okay, so under static condition, if you keep the plus minus parallel to the conductor, it will be short circuited. Okay, so whatever we discussed today, that is applicable only for static. Keep that point, it's for static. And the other condition is to electric field to survive, it should be always perpendicular to the conductor. So simple logic is you can consider a capacitor where it is survive only between the two plates. It is not survive parallel to the plate. It should be perpendicular to two plates. Right? That's you can understand from here. Now, hope you understand this. This too is sufficient. Now, same way, let us apply this and now let us write the equation. At least now you can suggest me the equation. What is Et1 equal to Et2? What will be the equation here? It's a free space, that's all. Anyhow, both sides it is dielectric, so electric field should exist. Nowhere should be zero. So same condition is applicable. Et1 equal to Et2. That's all. Same way here, dn1 equal to dn2. Or if you write in terms of electric field, then you can write on medium 1, you need to careful here. In medium 1, it is relative permittivity is 1. So epsilon r1 into En1 equal to medium 2, it is free space. So epsilon r equal to 1. So 1 into En2. So it's not really something different. If it is free space, just substitute epsilon r equal to 1. Then you will reach the or you will get the equations for free space condition. That's all. I will write the equations, consolidate the equations here for the above three cases. Tangential this is for A, B, C. Three cases. For three cases, I'm writing respectively. A tangential component of electric field should continuous across the boundary, and normal component of electric flux is continuous across the boundary. From this, you can write dt1 by epsilon r1 equal to dt2 by epsilon r2. Right, and from this you can write epsilon r1 into en1 is equal to epsilon r2 into en2. So it's just you are applying the relationship, that's all. But still you need to calculate these components. So don't think like this is more than sufficient, but from that still you have to derive this. We have to find this equation. So second combination, it is conductor. So et2 equal to et1 equal to 0. That is on the medium to electric field is 0. Okay, so you can put dt1 over epsilon r1 equal to 0, or you can say tangential electric flux equal to 0. Same way here, dn1 equal to 0 or en1 equal to 0. Guys, one thing I forgot to, okay, let me take the other possible formula. This is the formula 1, and other formula is dn1 minus dn2 equal to rho s. Now let me consider the equation dn1 minus dn2, where dn2 is 0, right? So equal to rho s. In the last class, while discussing one 2-mark question, like a small point where surface charge density is given and you are asked to calculate the electric flux density. Okay, there I'd suggest you like surface charge density, the unit is coulomb per square meter area, and the unit of electric flux density is also coulomb per square meter. Okay, so both are equal. Okay, so you can take this equation. It's really important. dn equal to rho s. Electric flux density normal to a given surface is equal to the surface charge density. I think this equation is evident from if you apply this condition, that is one side there is a metal and the other side there is a dielectric medium. It is like a metal above which there is some dielectric medium. In that case, what will be the electric field? Then finally, in this case, for dielectric and free space condition, same equation is applicable. Et1 equal to Et2. So dt1 by epsilon r1 equal to dt2 by this denominator is 1. That's all. Same here, dn1 equal to dn2. So epsilon r1 into en1 equal to epsilon r2, that is relative permittivity of air is 1. Then you will get en2. That's all. If you consider this third equation, or if you consider the surface charges, then you can write epsilon r1 into n1 minus en2 equal to rho s. Any questions, please?
No, sir.
Okay, next
Yes.
class we'll solve one problem based on this, and we can close this chapter. This is the third chapter as per your syllabus. So this third chapter is about electric field in material space, where we consider the materials and we have calculated the conditions for electric field which need to satisfy across the boundary, or sorry, at the boundary. So if on one side of the medium, if you know the electric field, then you can calculate what will be the electric field on the other side. Thanks for joining, Meeli. Now, so keep that point. This next class, there are no class, only busy schedule. Syllabus is Cat 1 syllabus, entire Cat 1 syllabus. I will share you further details in
Okay.
Teams. Okay, thank you.
Thank you, sir.